Good morning. Today, let's discuss a few problems and a few topics from probability. Question: there are 19 possible outcomes. 11 are favorable to select a boy, and 8 are favorable to select a girl. So here you can find two events, that is to select a boy and select a girl. So here you can find a few answers like what's the probability to select a boy? What's the probability to select a girl? What is the probability to select a particular boy? What is the probability to select a particular girl? Or to select a particular child? So these are a few questions you can identify from this question. Okay, so to select a boy, it's very simple. We have 8 boys. Among that, you have to select one boy. So favorable outcomes is 8 and the total is 19. So probability of selecting a boy is 8 by 90. Sorry, not 8, it's 11. 11 by 19. And probability of selecting a girl is 8 by 19. But probability of selecting a particular boy is 1 among 19. A particular boy is one boy among 19 students. Similarly, a particular girl is also 1 among 19. And a particular child is also 1 among 19. So when you consider a particular boy or a particular girl or a particular child, we get the same probabilities. So such conditions can be called as equiprobable. Equiprobable. Okay. So the events such as selecting a particular boy or a particular girl or a particular child are equiprobable events. Equiprobable events. Now let's roll a die and consider the following events. Event A is the result is an even number, and event B is the result is an odd number. So here you can find two events which we required. Result A is the outcome is an even number, and B is the outcome is an odd number. Okay, let's see. So A is 2, 4, 6, and B is 1, 3, 5. These are the possible events occur for A and B. And when we consider these two events, it's very clear that these two events never happens together. So our result never happens together. Result may either A or B. The result may either A or B. Why I'm saying this one is, let's take two more events. Like P is an event, set of odd numbers. After rolling a die, we have to get P as odd numbers and Q as factors of 5. So when you consider these two events, P as set of odd numbers and Q as factors of 5, let's see what are the numerals formed here. Set of odd numbers by rolling a die is 1, 3, 5. And you know factors of 5 when you roll a die is 1 and 5. So when you consider these two events can happen together. Even P and Q can happen together, because after rolling a die, if you get the result as 1, even P is true, even Q is also true. So in this example, both these events can happen together. But here in this example, either A or B can happen at one time. Okay, so here both the events cannot happen together. Both the events cannot happen together. Then such events are known as mutually exclusive events. Okay, so here these two events are mutually exclusive events as they cannot happen together. And here these two events can happen together, so we can call them as not mutually exclusive events. They are non-mutually exclusive events. If two events are mutually exclusive events, then A intersection B means the common region for A and B. Is there something common? No. So A intersection B will be null set when two events are mutually exclusive events. And this is a condition we use to verify whether two events are mutually exclusive. Suppose two events are given, you want to check whether they are mutually exclusive. In such case, we have to find A intersection B and verify whether it is null set. If it is null set, the events are mutually exclusive. If it is not null set, the events are not mutually exclusive, like previous example. In previous example, P was set 1, 3, 5 and Q set 1, 5. So if you take P intersection Q, it is set 1, 5, which is not null set. So these two events are not mutually exclusive events. But here these two events are mutually exclusive events. And if the events are mutually exclusive or not mutually exclusive, we can use a law known as addition law. Addition law for mutually exclusive events is probability of A union B. The addition law for mutually exclusive events is probability of A union B is probability of A plus probability of B. This law is actually derived in set theory. There it was number of A union B was number of A plus number of B. This is the law we used in set theory if two sets are disjoint sets. If two sets are disjoint sets, the number of A union B is number of A plus number of B. So the term disjoint and mutually exclusive events are giving us the same idea, in which A intersection B is null set. So when you make this one as a Venn diagram, we get it like A intersection B is null set. There is no intersection region for that. Okay. And if the events are not mutually exclusive, if the events are not mutually exclusive, that means if A intersection B is not null set, then addition law is probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. This is a law when the events are not mutually exclusive events. Then probability of A union B. Then addition law states that probability of A plus probability of B minus probability of A intersection B. And if A intersection B is null set, that means if the events are mutually exclusive, then probability of A union B is probability of A plus probability of B. Remember these two cases, and this is a condition to check whether the events are mutually exclusive. One digit is randomly selected from 1, 2, 3, 4, 5, 6, 7, 8, 9. Three possible events are a multiple of 3 is selected, B, a factor of 8 is selected, and C, a primary number is selected. In this question, let's write the set form of A. A multiple of 3 is selected. So from this multiple of 3, here we have to consider this one as universal set. So first let's write universal set, which is 1, 2, 3, 4, etc. up to 9. A is a multiple of 3. Multiple of 3, 3, 6, 9. B is a factor of 8, which is 2, of course, factor of 8. 1, 2, 4, 8. C is a primary number. So which are the prime numbers you find? 2, 3, 5, 7. Okay, so here we can find the probability of A, probability of B, and probability of C separately. So what is probability of A here? It is 3 out of 9. 9 numbers are there. So 3 out of 9, or 1 by 3. And probability of B is 4 by 9. And probability of C is also 4 by 9. Now our task is to find out probability of A union B. We want probability of A union B as first question. So to check or to find out probability of A union B, we have to check whether the events are mutually exclusive. We have to check whether the event A and B are mutually exclusive. So how do we check? To check whether they are mutually exclusive, we need to verify A intersection B. So check A intersection B. Do you find anything common in A and B? No. So A intersection B is null set. That means event A and B are mutually exclusive. So we can write probability of A union B as probability of A plus probability of B, which is equal to 1 over 3 or 3 by 9. That's better for us. 3 by 9 plus probability of B is 4 by 9. So we get the answer as 7 by 9. Okay. If you want to find probability of A union C, if you want to find probability of A union C, we need to check A intersection C. Check A intersection C. Do you have anything common? Yes, what is A intersection C? Set 3. Only one element is common, that is 3, isn't it? So probability of A intersection C is 1 by 9. Probability of A intersection C is 1 by 9 because there is one element in A intersection C. So A intersection C is not a null set. So we can write probability of A union C as P of A plus P of C minus P of A intersection C. That's equal to 3 over 9 plus 4 by 9 minus 1 by 9. We get it as 6 by 9 or 2 by 3. Even instead of using P, we can find the number directly. After finding the number, finally we can find P. That also possible. Okay. Another question what we can expect is P of B union C. So for that we need to check B intersection C. That means whether B and C are mutually exclusive. So when you find B intersection C, there is how many elements? Only one element is common. That is 2. So probability of B intersection C is 1 by 9. Even I will show you with number how to do. Okay. So as B intersection C is set 2, the number of B intersection C is 1. So we will find number of P union C is equal to number of B plus number of C minus number of B intersection C. That's equal to number of B. B has 4 elements plus C has 4 elements minus B intersection C has 1 element. We get 4 plus 4, 8. 8 minus 1, 7. Therefore, now probability of B union C is B union C has 7 elements out of 9. So we get probability of B union C as 7 by 9. You can use this method or directly probability method. No issue. So this is one of the examples you can find from mutually and not mutually exclusive events. Another question. A certain horse has a 70% chance of winning any particular race. Find the probability that it wins exactly one of its next 2 races. So a certain horse has a 70% chance of winning a particular race. So from this sentence we can find the probability of winning the race. Let it be P of W is 70%. 70% is 0.7. That means probability to lose is 0.3, which is 1 minus 0.7. 0.3. Okay, and for doing this question, it's better to make a tree diagram so that we can make the things very clear. Okay, so if you make a tree diagram for this question, in the first race, the horse has a chance to win or lose. If it wins, the probability will be 0.7, loss 0.3. So this is the chance of first race. And when it goes for the second race, because we have to take care of 2 races. If the horse wins the first race and goes to the second one, there is a chance of either win or lose with probability 0.7, 0.3. Similarly, if it lost the first race and goes to the second race, also have 2 chances. It is either to win or lose with probability 0.7 and 0.3 respectively. Okay, so we got the proper tree diagram. Now let's see the question. Our question is, it wins exactly one of its next 2 races. So before going for this question, let's check the second race. Does the result of second race based on first? Is the second result is affected by the first one with the first one? Is there any connection between these 2 results? No. The second win or lose not depending upon the first one. That means these 2 events, so we have 2 events here. First race and second race are the 2 events. First event is first race, second event is second race. So these 2 events are occurring without being affected by the occurring of other. Okay, and such type of events are called as independent events. Means 2 events are said to be independent if either can occur without being affected by the occurrence of other. So 2 events are said to be independent if either can occur without being affected by the occurring of the other. Okay, so if the events are independent, we have to make use of a law known as multiplication law. Like, recall, if the events are mutually exclusive or not mutually exclusive, there we used addition law. And if the events are independent, we can use a law known as multiplication law, which states that probability of A and B. So in this case of independent events, 2 events are occurring. That is A and B. We are thinking about first race and second race. We have to think about the result of first race and second race in such a way that events are not depending each other. Can be mentioned as probability of A intersection B. So intersection is for the connective and, union is for the connective or. We have learned the same in set theory also. Is P of A multiplied by P of B. So remember, probability of A and B, or probability of A intersection B, is equal to probability of A into probability of B. This is the same rule we use for dependent events also, but with certain changes. Okay, so when we discuss about dependent events, we'll go through that. Okay. So in this question, we required probability that it wins exactly one of its next two races. We required exact one win, not even two wins. We want exactly one win of the next two races. So when you see the tree diagram, you can find out, if you find the first branch, here you find win and win. That means there are two wins, but we want only one win. So when you see the next branch, win and loss. So this is a possible one for us. So we have to find probability of win and loss. Or when you go for the next branch, we can find lose and win. There are also exactly one win. So probability of lose and win. When you see the next branch, fourth one, it is loss and loss. There is no win in that. So our required parts are probability of win and loss, or probability of lose and win. See, this answer you can find out here itself, okay, directly. But here to show you, probability of win and lose is probability of win multiplied by probability of loss, or plus probability of loss multiplied by probability of win. That's equal to 0.7 times 0.3 plus 0.3 times 0.7. Do the calculation, we get the result as 0.42. A coin is biased such that the probability that three tosses all result in heads is 125 divided by 512. Find the probability of obtaining no heads with three tosses of the coin. So here one of the main factor you have to identify is a coin is biased. If we use a fair coin, an unbiased coin, it gives the probability of each face as 1/2 in theoretical probability. If a coin is unbiased, or if a coin is a fair coin, it gives the probability for head is always 1/2, and probability for tails is also 1/2 in theoretical probability. Okay, and even it is in experimental probability, there is a chance of getting equal faces. But here, as the coin is biased, we cannot expect equiprobable events. Okay, and here it is mentioned that means we cannot consider the probability of coin is 1/2 for getting head or tail. So here our main task is to find the probability of each side. For that, let's use the first sentence. This is the first given condition. Three tosses all result in heads. So when we made three tosses, all the three tosses gave a result as 125/12. Okay, so to avoid this writing always heads and tails, let's assume probability of heads as what we will say H, and probability of tail as T. Okay, so here as per the result we have probability that all the three tosses result in heads. That means probability of head and head and head. Even we no need of this assumption. Let's make it like this. This is enough. Okay. So what they have given is probability of three tosses result in heads. All the three tosses are heads. That means probability of head and head and head is 125 by 512, which is probability of head into probability of head into probability of head, as the events are independent, is 125 by 512, which is probability of head the whole cubed is 125 by 512, or we get probability of head is cube root of 125 by 512, which is equal to 5 by 8. So now we got probability of head as 5 by 8. So now we can find probability of tail is 1 minus 5 by 8. As we know, the total probability is always 1. So probability of tail, that means we can say probability of head and probability of tail are two different events that gives the result 1 always. That means probability of head plus probability of tail gives us the result 1. These kinds of events are known as exhaustive events. Exhaustive events. That the events in which they take all the possible values of the experiment. Okay, so here we get probability of tail as 3 by 8. Now result what we required is probability of no heads with 3 tosses. So the result what we required is probability of no heads. That means probability of tail and tail and tail, which is P of t times P of t times P of t. And you know P of t is 3 by 8. So when you multiply it 3 times, we get 3 by 8 the whole cubed, which is equal to 27 by 512 as result. In coming classes, we include more problems related to biased questions like biased coin, biased die, etc. Okay, thank you.